Something that I didn't really emphasize enough, really, is that with these equations that have two variables, the equation itself is establishing a relationship between the variables that appear, no matter what labels they might have, X and Y, or R and Q, whatever the case might be. The equation is one version of, here is a relationship between these two things. And the equation really is not necessarily super helpful to us unless we need to do something that might use that equation. As far as really describing that relationship, it's not something that's easy for us to really get a hold of, really grasp and understand or see. So the idea of making a drawing based on our equation gives us a way of graphically, visually representing what that relationship looks like. So slope, the steepness, where that line might appear. Is it further over here on our grid? Is it further down here? Wherever it might be. Where does that line end up appearing? What does it look like? So the slope tells us a little bit of what it looks like, but only so far as how we would travel along that line. So we could have something like this, we could have something like this. How do we tell the difference? We'd have to have a location that basically ties down our line into a particular location on the grid. Is it this one? Is it this one? Is it something else, somewhere else on the grid? And for that, we would need a point. We would kind of need a starting place, you could say. We would need an anchor. So as far as that goes, we mentioned that the nice version of our equation was called the slope-intercept form. The intercept word is referring to what is called a Y-intercept. Well, a Y-intercept sort of suggests that there might also be a thing called an X-intercept, and those names as well sort of give a little hint as to what they are. And they are going to be points, particular types of points, and either the X-intercept points that would be on our X-axis, or the Y-intercept points that would be on our Y-axis. We might not have one of these. We might not have both of these. We might not have, or we might have both of these as well. So, we've just got to have that flexibility with our definition. And also, because lines aren't the only sort of relationship that we might have between two things, these definitions open us up to all different other kinds of relationships by saying there might be one, there might be many, there might be one, there might be many. So what we have is a much more generic definition for these that we can use as we branch out to other kinds of relationships, other kinds of equations. But for right now, dealing with lines, well, things are going to be pretty limited in the way that they end up appearing. By using the slope and the Y-intercept, we have a much nicer way of being able to create these drawings. You could say we have a more elegant way of doing things, and largely it is, well, it's less time consuming. The other alternative would be going back to that very basic idea of trying to find a pair of numbers that make our equation true, then eventually finding another pair of numbers that make our equation true, so that I can now play connect the dots. And, well, what if I didn't have one of or both of those pairs correct? I wouldn't have the right picture to create. So this idea of having to go through this more exhausting and exhaustive process of finding enough points to be able to play connect the dots, this is really a method of last resort. Because it is so time consuming and it's really inefficient, it's inelegant. So much prefer an elegant, efficient manner of doing things. So the X-intercept, the Y-intercept, these might be helpful things for us. And again, from our earlier comment, that brief offhand comment, the Y-intercept is the one that actually is the more useful. But we want to mention both simply because there are occasions where we need X-intercepts. There might be even occasions where we are forced to create a drawing by specifically finding both X-intercept and Y-intercept points in order for us to do our connect the dots. So we might not actually have the freedom to use our most efficient method of working with the Y-intercept and the slope. We might be forced to do something like this particular example, find those intercepts, and then what we're not going to do here, which is use those to create the drawing. The X-intercept has every single time a nice starting place for me. The X-intercept, basically I'm looking for an X. That means I have to know something about the Y, and it's always the same thing. It's that the Y is 0. So if I want the X-intercept, I'm looking for an X. That means I have to know something about the Y, and the Y is 0. This is an established fact that I can just use. I want to commit that to memory, and it gives me a nice quick jumping off place to start doing my work, put in the 0 for Y, solve for X, and give the pair, and it would always be a something, comma, 0. The Y-intercept, I actually can flip-flop those comments. Y-intercept means I'm looking for the Y number. That means I have to know something about the X. It's 0. Which gives me a nice starting off place, putting in the 0 for X, eventually solving for Y, and then I would want to give both of those paired up together because the X and Y intercepts, these are points, which means that they're ordered pairs. They're now one number, it's a pair of numbers. So those Y-intercepts, they're always going to be 0, comma, a number. So those nice sort of facts give me a good jumping off place to try to make things at least as nice as possible for those situations where I have to find the X and Y intercepts. So let's actually do an example from start to finish where we also then would graph, we would draw in what this particular line is going to look like. So if we begin with the X-intercept, you don't have to, but that's just kind of alphabetically how it goes. The X-intercept, again, the nice plain fact is that Y is going to be equal to 0, and that means that in our equation, we would have 7 times 0 minus 14x equals 28. So we would have the negative 14x equals 28, giving us x equals negative 2. So negative 2, comma 0 is the X-intercept. The Y-intercept, we're going to flip-flop the comments that we've made here as we start doing our work. That means we're going to be looking for the Y number when X is 0. And that means in our equation we would have 7y minus 14 times 0 equals 28. So 7y is equal to 28, giving us y equals 4. So the y-intercept would be 0, comma 4. Now we've got those two that we can use. We want to pinpoint those in our grid and then play connect the dots. So we are going to use the comments that we mentioned in the previous video about how we would locate these. So let's go ahead and lock in some markings on this grid And let's just keep things simple and go by ones. So each of these little markings are going to be one step or one unit. So if we were looking to lock in our X-intercept, and let's even use the same color that we had used in the previous example, our X-intercept, -2, 0. The first number tells us whether we're going to go to the left or to the right. Because that first number is negative, our negative numbers are to the left. So we would begin by going from the center, the bullseye of our grid, 2 spots, 2 steps, 2 units to the left. The second number is a 0, which means, well, we do not go up or down. We take 0 steps. So the pink point is going to be exactly where my finger is pointing right here. It's going to be on the x-axis, as it darn well better be, given that we were talking about an X-intercept. I better be intercepting my x-axis when I put that point. And, oh, we're using purple for that one. Purple for that one. So the Y-intercept, let's put that in purple. And the first number is a 0. So that means starting from my central location in the grid, the origin is what we officially call it. Starting from the origin, starting from that bullseye mark of my grid, I do not move to the left or right. The second number is a 4. So the second number telling us to move up or down, because it's a 4, that's positive, that's up. So I'm going to put my purple point right here, where my finger is pointing. Now that I've got those 2 points locked in, I can go ahead and play connect the dots and draw in as neatly as possible a nice big long line, trying to make that as straight as possible. With this particular example, we can also bring up a little something with the slope that we didn't really mention directly in the other video. If I have a picture, I can get the slope by doing the rise over run sort of idea. And thinking of how we talked about those directions before, we said we always like to start out with going to the right. So as far as the pink and the purple, the pink point is to the left. We would move to the right to get to our purple point. So we would move to the right 1, 2 steps. And then we would move up 1, 2, 3, 4 steps. So the rise, 4, the run, 2, just to be sure. +4 for the rise. +2 for the run. That would allow me to build my slope. +4 divided by +2 gives me a slope of 2. Doesn't have a bottom number when I just nice and simplify like I normally would. But remember that with a fraction version of the number 2, I have an over 1 that I can put in there if I really want to. So if I have figured out my slope is most simply the number 2. What that could mean for me instead is that I would say 2 over 1, aka 2 steps up, 1 step right. 1 step right, 2 steps up. Hey, I did a pretty good job drawing that one. 1 step to the right, 2 steps up. I could switch those directions as well, though, and say that I could go 2 steps down, 1 step left, 1 step left, 2 steps down. So again, I got a lot of flexibility there in how I read and how I actually use that information. But because we have a picture here to work with and we hadn't mentioned slope already, it was a nice opportunity for us to talk about if we have a picture and they ask us for slope, we still use the same ideas as we had discussed in that earlier video about how the slope is going to actually relate to the line that we see, literally see, as far as this drawing goes. If we are specifically told that we have to, like in this example, use the intercepts, then these need to appear. If we do not use one or both of those, then we could be marked wrong because we were not following the directions. So something to keep an eye out for, any sort of extra part of the directions that might force you, pigeonhole you, into doing things a particular way. But if you have the choice, the recommendation that I have already mentioned, and let's go ahead and lay it out now very clearly, we'll use the slope and the y-intercept because we can get those two pieces of information, plink, plunk, straight from our y equals mx plus b, our slope-intercept form of the equation. If I can pick those two things out immediately, great. If I have to find them, well, again, this is still a little bit more efficient for us to work our way through than the other alternatives. So finding the slope-intercept form of the equation and then plink, plunk, picking out the slope and that y-intercept. The slope tells me how to move, but the y-intercept is what tells me the anchor place. That's what tells me where to lock my line in. So that's why that's mentioned first. Use the y-intercept as a starting point, and then the slope as a set of directions with how to move so that I can reach one or more points and play connect the dots. So using, hey, this looks familiar. This is the same equation that we had used in an earlier example where we had been asked only for the slope. You may in fact even remember the slope and how we got it, but just to repeat the steps here of how we got there. What we ended up seeing eventually is that our slope-intercept form was y equals 4/3, 4/3, followed by the letter x, followed by a -4. Having that slope-intercept form, let me move things around here for a second. That didn't work properly. Having things written down in slope-intercept form, we want the slope and the y-intercept. Going back to those comments, because the starting point literally is point, I'm putting the y-intercept first. In my equation though, as I read through the slope-intercept form, the name tells me the first thing I see is the slope. So in fact, I can go ahead and just fill in those blank places. The first thing that we see is the slope of 4/3. So we can go ahead and write that in. The slope is 4/3 coming from our slope-intercept form. And then the information that appears after the letter x is what connects with my y-intercept. Every y-intercept begins with a 0 comma, so the rest of that y-intercept is what we've highlighted there in turquoise that shows up after the letter X. So there are the two pieces of information that we can pluck directly out of our equation, directly out of our slope-intercept equation. And for our set of directions, it's worth noting, and let's go ahead and even write it down, that we have, and we'll do the same sort of thing that we've done before. The bottom number is positive. That means that we always begin with move right. The top number is positive, meaning that's going to be up. If we reverse that set of directions, then we would have left 3, and didn't need to put that in there, down 4. So we would want to go ahead and say start at the point 0 comma negative 4 and move right 3 up 4 and or, because we've got the choice of using that second set of directions, left 3 down 4, like Star Wars droids or something. So over on our set of X and Y axes, let's go ahead and put in some markings so that we can pinpoint our y-intercept and so that we can move according to the directions that come from our slope. Starting from the middle of that grid, the origin, starting from that bullseye of our target here, we're going to pinpoint our y-intercept. So let's go ahead and let's put that in blue so that it stands out for us. That means that from that central location, we do not move to the left or right. We do, however, move down 4 spots. Then we would want to move possibly to the right 3 up 4. So let's see if we can actually accomplish that. If we go from the blue point right 3 and up 4. Oh, hey, look at that. What a nifty little coincidence that we would end up arriving at that particular special location. There's our X-intercept. The other possibility is that from our blue point, we could move to the left 3 and down 4. 1, 2, 3, down, 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 down. This is not in our picture window, at least the way that we've drawn it right now. So this is not something that we can actually use with the size of the drawing that we're making. So I'm going to make a comment to that effect that this would be taking us off our picture window. So, the things that we have at least are enough for us to be able to draw in that line and just have something that kind of stands out for us. Let's just use that. Close enough for government work. There's the line that we needed to graph. So again, to run through this very quickly without having to stop and start with all of the different information. By finding the slope-intercept form, we can pluck out the slope, we can pluck out the y-intercept. We started our y-intercept, so we go ahead and pinpoint that location, and we use our slope, one set of directions, possibly the other set, in order to get at least one more point somewhere on our grid so that we can connect those two together. Now, as long as we're working carefully and we do that correctly, we're in good shape. So, just to go ahead and hammer that idea in a little bit more with one last example. Let's say that we've got the equation 6x plus 3y plus 9 equals 0, and we would like to graph that. So we're going to take the same sort of approach from the beginning. We would want to find the slope-intercept form. So we would want to eventually get our y equals mx plus b. We can start by getting the 3y by itself, and one version of doing so would mean that we would subtract 6x and subtract 9 on both sides. From there, we would want to divide on both sides by 3, meaning that we would want to take each individual term and divide by 3. This would give us y equals negative 2x minus 3. As far as creating our drawing, the y-intercept is where we would start doing our drawing, and the slope is going to give us our set of directions. But as we're reading through that equation, the slope is the first thing that we see. In between the equal sign and the letter x is our slope, negative 2. Going back to the earlier comment, the fraction version of this would be negative 2 over 1, meaning that our directions, starting with the bottom number, right 1, the top number is negative, so down 2, or we could have the reverse set of directions, left 1, up 2. So we can now go ahead and write in our y-intercept. Y-intercept always begins with 0, comma, and the number that shows up after the x is a negative, so negative 3. We can take this information, move over to our axes, put in some markings. Start by identifying the location of our y-intercept, which would be from the bullseye down 3. So from that origin, from the middle of our grid, don't move to the left or right because the first number is a 0 in that pair. Move down 3 because the second number is negative 3. Now that I'm locked into that particular location, I can try to use one or both sets of directions in order to come up with other points that would be on the line that I want to draw in. So if I can move to the right 1 and down 2, I can. I couldn't move to the right 1 and down 2 again, but I can just barely fit that one in that particular spot. Just to show you the other set of directions working for us, we actually have room to use those if we start at our y-intercept and move to the left 1 and up 2. If we move to the left 1 and up 2, and we even have more room, we can move to the left 1 and up 2 again, and left 1 and up 2 again, and left 1 and up 2 again. We can actually put in several more points that appear on this particular line by using that set of directions several more times. We do not need to do this. This just gives us an abundance of points for us to play connect the dots. Any two of these would have worked, so the y-intercept and the very first dot we marked, the y-intercept and the third dot that we marked, it doesn't really matter. But I did want to show you that you have that sort of freedom involved. So just having all of those in there helps me try to get things lined up properly and draw my line in there. So there is the line for the equation 6x plus 3y plus 9 equals 0. Finding the slope-intercept, y equals mx plus b. Using that slope and y-intercept information to be able to come up with the starting point for doing my drawing and the directions for how to finish my drawing. The starting point is my y-intercept. The directions provided by my slope tell me which way to move in order to create the line that I am looking to draw in. The more points that I can create, the nicer it might be for me to draw these by hand. And there we go. If you have instead an equation that is one of our special types, the horizontal line y equals a number, or the vertical line x equals a number, then in that case, simply remembering what those equations look like, which special type of line they're associated with, allows us to very quickly make those kinds of drawings. So if they told us that we needed to draw the line for the equation y equals 4, well, y equals 4 corresponds to a horizontal line. Y equals 4, well, y equals 4 is right here. I would draw in a horizontal line, and I'd be done. If they told us you need to make a drawing for x equals -8, well, all right, x equals -8 means that I've got a vertical line, so I would go out to where x is equal to -8 and draw in a vertical line, and then that one would be done. So those special kinds of lines, much nicer and quicker for us to deal with. The ones that are more time consuming would be like these past two examples that we did. So y-intercept is our starting point. The slope tells us how to move in order to actually execute the drawing of that line. And that's all we need to do.